questions began emerging almost immediately after the powerful earthquake struck south of Mindanao. Why were stretches of shoreline no longer where maps said they should be? Why were coral reefs, once hidden beneath seawater, suddenly exposed to the tropical sun? Why did local residents find themselves walking across ground that, only days earlier, had been part of the sea? The answers did not come from speculation, but from observations made along the coastlines facing the Sarangani Sea after the magnitude 7.8 earthquake that occurred on June 8, 2026 Philippine time. Initial aerial assessments revealed something remarkable yet entirely consistent with the forces that shaped the planet. In several coastal sections of Glan in Sarangani province and parts of Jose Abad Santos in Davao Occidental, the ocean had not truly disappeared. Instead, the land itself had risen. The change was so significant that some shorelines appeared to have retreated by roughly 200 meters, or about 656 feet, while portions of the coast were estimated to have been lifted approximately 2 meters, or about 6.5 feet, above their previous elevation. For communities accustomed to measuring change over decades, the transformation occurred in minutes. The earthquake responsible for the coastal shift was recorded at magnitude 7.8 and occurred approximately 26 kilometers, or 16 miles, southwest of Cablalan in the southern Philippines. According to seismic data, the event originated at a depth of approximately 55 kilometers, or 34 miles. It resulted from thrust faulting within one of the most complex tectonic regions on Earth, where multiple plates and microplates interact as the Philippine plate moves westward beneath the Sunda plate. While earthquakes are often represented on maps as single points, a magnitude 7.8 event is anything but a point. Such earthquakes typically involve movement across a fault surface, extending roughly 120 kilometers in length and 50 kilometers in width, equivalent to approximately 75 miles by 31 miles. Across that enormous area, sections of the Earth's crust can move upward, downward, or horizontally by several meters in a matter of seconds. The consequences are not limited to shaking. In coastal regions, the vertical movement of the seafloor and adjacent land can permanently alter the relationship between land and sea. Ports may become shallower. Coral reefs may emerge from the water. Tidal zones may shift. Areas once submerged during high tide may remain permanently dry. In some cases, coastlines move seaward. In others, they retreat inland. The changes depend entirely on the geometry of fault movement beneath the surface. The June 2026 earthquake appears to have produced one of the most visible examples of coastal uplift observed in the Philippines in recent years. Aerial surveys conducted several days after the earthquake documented extensive sections of newly exposed reef platforms. Corals that had existed underwater for years were suddenly visible above the surface. Along portions of the shoreline near Barangay Pangyan in Glan, the sea appeared to have withdrawn dramatically. To observers unfamiliar with tectonic uplift, the scene resembled a coastline abandoned by the ocean itself. Yet the water had not permanently retreated. The apparent disappearance of the sea resulted from the sudden rise of the coastal platform. The ocean remained at essentially the same level relative to the center of the Earth. The land, however, had been pushed upward by powerful geological forces operating deep beneath the surface. This distinction is important because it reveals the extraordinary scale of energy released during major earthquakes. When tectonic plates converge, they do not slide smoothly past one another. Friction causes sections of the plate boundary to become locked. Over years, decades, or even centuries, stress accumulates as the plates continue attempting to move. Eventually, the stored strain exceeds the strength of the rocks holding the boundary in place. When failure occurs, the accumulated energy is released almost instantaneously. The result is an earthquake. In thrust fault earthquakes, one block of crust is forced upward relative to another. Where the fault reaches beneath coastlines or offshore regions, that upward movement can extend to the seafloor and adjacent land areas. The tectonic environment surrounding Mindanao is particularly complicated because it sits within a region where several interacting plates accommodate the broader convergence between the Philippine Sea Plate and the Sunda Plate. The area does not behave as a simple boundary between two rigid plates. Instead, numerous smaller tectonic blocks absorb and redistribute motion throughout the region. At the location of the June earthquake, the Philippine plate moves toward the Sunda plate at approximately 7.3 centimeters per year, equivalent to nearly 3 inches annually. Although that movement seems insignificant on a human timescale, over decades it accumulates enormous strain. The release of that strain during a magnitude 7.8 earthquake can reshape coastlines in ways visible from aircraft and satellites. The newly exposed coral reefs provided some of the clearest evidence of uplift. Coral organisms survive within specific depth ranges where sunlight penetrates seawater. When tectonic uplift suddenly raises a reef platform above sea level, living coral colonies may become stranded in the air. The resulting reef surface serves as a natural marker of how much vertical displacement occurred during the earthquake. In many parts of the world, ancient uplifted coral terraces provide geological records of repeated earthquakes stretching back thousands of years. Each terrace represents a former shoreline elevated by tectonic activity. The fresh exposure of reefs in Sarangani and nearby coastal areas may become another chapter in that long geological record. The observed shoreline retreat of approximately 200 meters is equally significant. Such a shift does not mean the ocean permanently moved away from the region. Instead, it reflects the creation of a broader coastal platform following uplift. Areas once covered by shallow water became dry land, effectively extending the coastline outward. For local communities, these changes can create immediate practical challenges. Fishing areas may be altered. Boat access routes may require adjustment. Navigation channels can become shallower. Coastal ecosystems may experience sudden disruption. Mangrove zones, seagrass beds, and coral communities are often highly sensitive to rapid changes in water depth. Infrastructure can also be affected. Wharves designed for previous water levels may no longer function as intended. Small harbors may require dredging or redesign. Coastal drainage patterns may shift. Areas that once flooded during high tides may remain dry, while neighboring locations may experience entirely different water flow conditions. These consequences highlight an often overlooked aspect of earthquakes. Public attention frequently focuses on ground shaking and structural damage, yet major earthquakes are also capable of permanently modifying landscapes. Mountains rise through repeated episodes of uplift. Valleys form through tectonic deformation and erosion. Coastlines advance and retreat over geological time through countless individual events. The June 2026 earthquake provided a reminder that some of those changes can occur within moments. The Philippine archipelago, positioned within the seismically active Western Pacific, has experienced similar tectonic processes throughout its geological history. Many islands owe their existence to long-term tectonic uplift. Some coastal terraces visible today were created through repeated episodes of earthquake-driven deformation over thousands of years. The Sarangani Sea earthquake appears to have added another measurable increment to that continuing process. Satellite observations are expected to play an important role in documenting the full extent of deformation. Modern radar satellites can measure ground displacement with remarkable precision. By comparing images collected before and after an earthquake, scientists can determine where the surface rose, sank, or shifted horizontally. These measurements often reveal deformation patterns extending far beyond areas visible from the ground. A coastline displaying 2 meters of uplift may represent only one part of a broader deformation field, spanning hundreds of square kilometers. Offshore regions may also have experienced significant vertical movement, though such changes are more difficult to observe directly. Understanding the complete pattern of uplift and subsidence is essential for evaluating future coastal hazards. Changes in coastal elevation can influence tsunami behavior, storm surge impacts, and long-term shoreline evolution. Areas raised above sea level may gain protection from certain flooding events, while neighboring regions that experience subsidence can become more vulnerable. The relationship between earthquakes and tsunamis further underscores the importance of vertical displacement. Not every major earthquake generates a destructive tsunami. The determining factor is often the extent and location of seafloor movement. Significant vertical displacement beneath the ocean can push enormous volumes of water, initiating tsunami waves that travel across entire ocean basins. Although the June 2026 earthquake generated concern because of its offshore location and large magnitude, the observed coastal uplift primarily illustrates the broader geological mechanism responsible for both tectonic deformation and tsunami generation. The newly emerged shoreline sections offer direct evidence that substantial crustal movement occurred. From a geological perspective, the event demonstrates the immense power of plate tectonics operating beneath the Philippines. The region sits within the Pacific Ring of Fire, a vast zone of seismic and volcanic activity surrounding much of the Pacific Ocean. Along this belt, tectonic plates continuously collide, separate, and slide past one another. The Philippines occupies one of the most complex sectors of that system. Rather than lying along a single plate boundary, the country is influenced by multiple interacting tectonic structures. These interactions create numerous active faults, trenches, and deformation zones capable of producing large earthquakes. The June earthquake occurred within that intricate framework. Its magnitude reflected the release of strain accumulated through years of plate convergence. Its coastal effects revealed how that released energy can reshape landscapes. Its uplifted shorelines provided visible evidence of forces usually hidden deep underground. For residents observing exposed reefs and newly expanded beaches, the changes may appear unprecedented, yet on geological timescales, they represent one episode in a continuing process that has shaped the Philippine archipelago for millions of years. Each major earthquake leaves an imprint on the landscape. Some create scarps across valleys. Others raise mountain ranges. Some alter river courses. A few transform coastlines so dramatically that familiar geographic boundaries must be reconsidered. The Sarangani Sea earthquake belongs to that category. Its legacy will not be measured solely by seismic records or instrumental readings. It will also be measured by the stretch of coastline that emerged from the sea, by the coral reef suddenly exposed to daylight, and by the permanent alteration of the boundary between land and ocean. Maps may eventually be updated. Shoreline surveys will refine measurements. Additional studies will determine the precise extent of uplift across the region. Yet the essential fact is already clear. A section of the southern Philippine coast now stands higher than it did before June 8, 2026. The ocean itself did not vanish. Sea level did not collapse. The water did not permanently withdraw into deeper basins. Instead, a massive thrust fault earthquake lifted part of the coastline upward by roughly 2 meters, creating the striking impression that the sea had retreated and never returned. For geologists, the exposed reefs and widened shoreline represent evidence of crustal deformation. For coastal communities, they represent a new physical reality requiring adaptation. For the broader public, they serve as a powerful illustration that Earth's surface is not fixed. Even landscapes that appear stable for generations remain connected to tectonic forces operating far below. Most of the time, those forces move too slowly to notice. Occasionally, they reveal themselves through a single event capable of changing the shape of a coastline in less time than it takes to read a news bulletin. The June 2026 Sarangani Sea earthquake did exactly that. Along portions of Mindanao's southern coast, the boundary between land and sea shifted in a matter of moments, leaving behind one of the most visible examples of earthquake-driven coastal uplift in recent Philippine history. Days later, coral reefs stood exposed above the waterline, shorelines stretched outward by hundreds of meters, and a striking image emerged across parts of Sarangani and Davao Occidental, a place where the ocean seemed to disappear. Not because the sea went away, but because the earth itself rose to meet the sky. The longer-term implications of the uplift may prove just as significant as the immediate visual changes. Coastlines are dynamic environments even under normal conditions. Waves, tides, currents, storms, and sediment transport constantly reshape the narrow zone where land meets sea. When a major earthquake abruptly alters coastal elevation, those natural processes begin responding to an entirely new landscape. Areas that were previously submerged beneath several feet of water may now become permanent extensions of the shoreline. Newly exposed reef flats can change wave patterns and influence the movement of sediment along the coast. Channels once deep enough for small fishing vessels may become difficult to navigate, while entirely new tidal pools and shallow lagoons can form in places that did not previously exist. The ecological consequences may unfold over months and years. Coral reefs exposed above sea level often experience rapid stress because the organisms that build them are adapted to life underwater. Extended exposure to sunlight, heat, and air can damage or kill living coral colonies. At the same time, the uplifted reef platform becomes available for colonization by other coastal organisms. The transition marks the beginning of a new ecological phase rather than the end of an old one. Mangrove forests may also experience adjustments. These ecosystems occupy a narrow environmental range controlled by tides and salinity. Even relatively small changes in elevation can shift suitable habitat zones. In regions where the land rose significantly, mangrove communities may gradually expand seaward toward the new shoreline. For local fisheries, the changes may be particularly noticeable. Many fish species depend upon reefs, seagrass beds, and shallow coastal habitats during parts of their life cycles. Alterations in water depth can modify feeding areas, breeding grounds, and migration routes. Such changes do not necessarily mean a permanent decline in marine productivity, but they often require time for ecosystems to adjust to new conditions. The event also serves as a reminder that coastlines are not permanent fixtures on maps. Modern society often treats shorelines as fixed boundaries, yet geological records demonstrate that they are among the most mobile features on Earth. Sea levels rise and fall, rivers build deltas, storms erode beaches, earthquakes can instantly raise or lower entire sections of coast. Across the Pacific Basin, evidence of ancient shoreline changes is preserved in cliffs, terraces, and fossil coral deposits. Many of these features were created by the same process observed in southern Mindanao. An earthquake lifts a coastal area. Waves begin eroding the newly elevated shoreline. Over thousands of years, repeated episodes create stair-step terraces that record a region's tectonic history. The newly exposed coastal sections in Sarangani and Davao Occidental may eventually become part of such a record. Future generations examining the landscape may identify the uplifted reef surface as evidence of the June 2026 earthquake, just as geologists today identify ancient earthquakes through similar landforms elsewhere around the world. One of the most remarkable aspects of the event is the speed at which the transformation occurred. Geological change is often imagined as a slow process unfolding over millions of years. While that is true for many features, earthquakes demonstrate that significant landscape modification can happen almost instantly. The fault responsible for the earthquake accumulated stress gradually through plate motion measured in centimeters per year. Yet the release of that energy occurred in seconds. Decades of tectonic strain were converted into sudden movement, producing permanent changes visible from the air only days later. This contrast between slow accumulation and rapid release lies at the heart of earthquake science. The forces responsible for major seismic events operate continuously, even during periods when no earthquakes occur. The absence of shaking does not indicate an absence of movement. Plates continue converging, stress continues building, and deformation continues accumulating until another release occurs. The June earthquake provided a clear example of this principle. For years, the tectonic boundary beneath the region stored strain generated by the ongoing convergence of the Philippine and Sunda tectonic systems. The eventual rupture released enough energy to alter coastlines, trigger landslides, and generate measurable vertical displacement across parts of southern Mindanao. Aerial observations of landslides further highlighted the widespread nature of the earthquake's effects. When strong shaking affects mountainous or coastal terrain, unstable slopes can fail, sending rock and soil downslope. These secondary hazards often continue after the main shock and can contribute significantly to overall damage. Combined with coastal uplift, the landslides illustrate the diverse ways earthquakes reshape the environment. The effects extend beyond buildings and infrastructure. Entire landscapes respond to the sudden redistribution of stress within the Earth's crust. As additional surveys, satellite analyses, and field measurements continue, a more detailed picture of the deformation pattern will emerge. Scientists will map areas of uplift and subsidence, measure changes in shoreline position, and assess how much movement occurred along the fault. Such information will contribute to a better understanding of the tectonic processes operating beneath the southern Philippines. Yet even before those detailed studies are completed, the broad outcome is already evident. The earthquake permanently modified portions of the coastline. Coral reefs that once lay underwater are now exposed. Sections of shore have expanded seaward. The physical geography of parts of Sarangani and Davao Occidental is no longer exactly what it was before June 2026. That reality places the event among the most striking examples of recent earthquake-driven coastal transformation in the region. It demonstrates that tectonic forces are not abstract concepts confined to scientific reports or seismic instruments. They are active processes capable of changing familiar landscapes within moments. Along the shores facing the Sarangani Sea, the evidence remains visible. A visitor comparing the coastline before and after the earthquake would not merely see the aftermath of shaking. They would see proof that the Earth's crust moved, that the land rose, and that a boundary long assumed to be stable shifted in response to forces operating deep underground. The ocean never truly vanished. The water remained where gravity placed it. What changed was the land itself. Lifted upward by one of the strongest earthquakes to strike the region in recent years, the coastline emerged from the sea, leaving behind a powerful geological reminder that the surface of the planet is still under construction.